There, we are supercalifragilisticexpialidocious.
Hello everyone, I'm Joyce, and today we are going to show you how we build the electric clock. As this is a ODE project, we decided to build the clock by using electric circuit. In the following 16 minutes, we are going to show you how we do this project.
Hello everyone, before we start, make sure you've seen our how much is our outfit video. It's really fun and we're having a lot of fun filming that. So, well, let's get started for this project. Before we start heading into the clock, first we're going to talk about critic, that how we collaborated together to finish this project. First is Alyssa, who is known as the real-life hacker in our How Much Is Our Outfit video. She did all the theoretical analysis for the electric circuit that we designed, and she also plotted the report for us so that we can get the analysis information from her. And next is Yihua. You might reckon her as the future billionaire because she wore an extremely expensive mask in that video. But I cannot see what's the difference between the normal one. Well, she collects lectures and information online, and for us, and she also did the illustration for ODE Python animation. Next is for Ray. She plotted all the experiments and models, like the electric circuit design. She designs a really amazing electric circuit for the clock, and she also built the models like the LT Spice or Spice of Python and do the simulation for the entire circuit. And last is me, I'm Joyce, and what I did for this group is that I integrated all the informations that collected online or collected individually. I worked as a facilitator in this group that I can make sure what's new for this project for everyone and integrated everyone's thought together. Then I added the slide and video, included the how much is our outfit video for everyone. Next, we're going to see how we realized this idea. If we don't do anything, this wouldn't come true, so we need to do something to work it out. So first, next we're going to see how we realized the entire idea of the electric clock circuit. Well, if we don't do anything, then there's nothing we realize, right? So let's see how we do for this project. First of all, we need to collect or do some research for this topic. So we started to look around the literature or some papers on the internet because Google is always our friend, as we all know. So we read some of the relevant papers and essays online, and then we would find what it's used for, some useful information for us, and then we integrated together and taught each other. And second, we need to build models for the circuit because before we started to do an actual circuit, it's the best way to save time in case you did something that is not gonna work. Then you have to debug it, and it's just a waste of time. So we need to build models for ourselves to just theoretically prove that it might work in reality. And also by building models, we can think about what parameters we'd like to do research on, so we can find new questions by doing this. And next, we're going to build the actual circuit in reality. Of course, this project is aimed to building a new clock on our own. So, yeah. And by doing the experiments in reality, we can collect the experimental data so that we can use in our future. That is our next step. We have the comparison step. We have to compare the experimental data with the theoretical data that we calculate using our models or just calculate by our hand. Then this will be our final presentation. We have to integrate basically what we've done in this semester all together. Let's look at the first components that we used in our circuit. This is a really important component that we called amplifier. Well, you might start to think, what is this thing? It looks like a rectangle spider, right? It's kind of terrifying. You don't know what it is. Amplifier is basically a device that we can increase the power of a signal, and if you look at the patterns on the chart, then you would notice that the amplitude of wave would become bigger, and then this is what you see on the waveform. And you might start to wonder, what can we do if we apply the amplifier in the actual circuit? Well, it's basically we use amplifier to realize some mathematical calculation in our circuit, you've seen this in probably from elementary school all the way till your uni. And for the last one, it's really important when it explodes. If the amplifier just burned out, then it can just melt your breadboard. The temperature can goes up to I remember 250 degrees Celsius. It's really horrifying. So make sure you have to be careful while using it. And as for amplifier, now we started to and this is a simple this is an amplifier, and now I'm going to introduce how the amplifier works. And here we can see an amplifier has two inputs and one output. The two inputs has its name. They're individually called in the non-inverting input, and which is slide in the positive side, and we have in negative side, and we have the other input called the inverted input, which we slide it on the negative side. And here we have one output, and the only output that we call is that the only output we call it the V out, and we will write it in the form of VO. We've mentioned that the amplifier can help us to increase the power of our signals. So the power that increases in our signals, we give it a name, and it's called the voltage gain. As for the voltage gain, we can retain it as an A equals V out divided by V in, as we shown here. For the illustration on the left, we can see we have a voltage called the V diff. It is described as the difference between the voltage 1 and voltage 2. It should be 0 because, as you can see, voltage 1 and voltage 2 are connected to the ground. So the value of voltage 1 and voltage 2 should be the same, and we call this a virtual short. Just keep it in mind later because we're going to use it later. Now we're going to talk about the ideal operational amplifier and the non-ideal operational amplifier. Keep in mind the characteristic of the ideal operation amplifier because we are going to use it for the theoretical analysis in the following next 5 minutes. When I open the gain, you can see the gain of the circuit would goes to infinity, but if we give it a negative feedback on the output and the input voltage, then you can see we've highlighted here. The negative feedback here is here to stabilize the amp. Oh, here's a really important thing is that you have to keep in mind that the voltage gain for the V out is limited. The V out won't just goes up forever, no matter how high the input voltage is. It will still has its own saturation.
Hi guys, my name is Elisa. While all Ray said seems simple, we still needed to start from the basics, theoretical analysis. Here we have a circuit model designed by our team.
Are just labels for the measurements of voltage later. These two power supplies are just supplying power so that the op-amp will function. This is an LED or light emitting diode. It only allows current to flow from the top here to the bottom, which functions as filtering. Another usage of LED is for us to observe the current by seeing the light. So the rest is significant for us to analyze as the following. First of all, this whole circuit is called a RC feedback network, which means it is capable of producing its own input signal from the noise. This is why you don't see an input power supply other than these two. This is really cool because it is functioned by having the noises, which is not applicable in the ideal world. The non-inverting input terminal is connected between these two resistors, R1 and R2. According to the voltage divider rule, the voltage is in direct proportion to their resistance. We have V non-inverting equaling to V out multiplying by R2 over the sum of R1 plus R2. We use beta to represent it. Here we have a connected capacitor. To start, capacitor is a passive element that charges itself from the voltage supply when connected directly. In this case, it is charged from saturated output voltage through the resistors R3. Since capacitor stores and releases voltage from the circuit, whenever the absolute value of V inverting terminal is greater than or equal to the absolute value of V non-inverting terminal, output voltage will change to its opposing state, which we will demonstrate more clearly later. Now the signal is periodic. In this circuit, the period is 2 times the time constant RC, and multiplying the natural log of 1 plus beta divided by 1 minus theta. The subscripts are just showing which R and which C on the figure shown here. On the other note, we have chosen the values of R1 and R2 by design, so that the natural log here will be almost exactly the value of E, 2.714. So beta is about 0.461, and 1 plus 0.641 divided by 1 minus that is about 2.714. Taking the natural log of that would be about 0.999, which is close enough to 1. And this will cause an ideal period. In order to use this ideal period, we consider the reciprocal of that, which is the frequency to be used. Okay, after analyzing the circuit, you might still be wondering how the circuit produces what we want, and that is when Schmidt's trigger comes into play. The reason why this is called a trigger is because the output voltage retains its value until the input changes sufficiently to trigger a change. The line here is caused by having the initial condition of both voltage and current are at 0. It does not contribute much to our circuit as the LED will not respond during this change. So there will technically be 2 different kinds of threshold, the upper and the lower. First, the output voltage would be high due to the capacitor releasing the voltage. Then the output voltage will decrease due to the capacitor absorbing the voltage.
Hello, my name is Ray. I'm going to introduce things that help us simulate the circuit and analyze the data.
The first thing is SPICE. You might be curious why SPICE can help us simulate the circuit. It's not the SPICE that flavors the dishes. It is
simulation program with integrated circuit emphasis.
And today we are going to use LT SPICE, developed by Linear Technology. Here we have some familiar things, the abstract of LT SPICE on Wikipedia. Now I'll briefly demonstrate how to use LT SPICE. First, you can drag some components on the schematic, like resistor, diode, or capacitors, and draw lines. After drawing the whole schematic, we can just put some command, and here is the command, and push the run button. Then you can get the results, like the output voltage or the current through the LED. For the analyzing part and animation, we are going to use Matplotlib library and NumPy. But how do we combine them? Well, here we find something interesting. This guy deserves my star because he made the whole thing easier, and this is how the magic starts.
Pipe install LT SPICE.
I'm going to use Google Colab to finish the Python part. In order to use LT SPICE on Python, we need to pipe install LT SPICE and import the modules that we are going to use. According to the document of LT SPICE on Python, we need to set the file path and using these functions. Then we are going to use the functions provided by the LT SPICE Python to get the data. And we are going to use Matplotlib library to plot the voltage part. Here are the results. And we're plotting the time and current curve. And here are the results. And we use type function to get the data type. And we know that it's NumPy ND array, so I use shape to know the size of it. But here is the problem. The sample rate is not constant, and Yihuan will explain this.
After collecting data information, I conduct the animation by coding with Python based on the theory we analyzed, the model we built, and the graph we plot. I have 3 animations for you. But before we go into the animation,
to realize our animation, these are some key points to note. First, for each time sample, we define a function to store the data and plot it. Then, to animate, we use the form animation function to dynamically show the graphs. And for this function, we have parameter interval, so we can set different time intervals for updating the animation depending on situations. Another thing to know is that we notice that the time interval for getting data from LT spice is not constant due to concerns like optimization and the size of file. So before beginning to do animation, we first have to resample the time to make the interval a constant. Let's move on to our 3 animations.
I would like to show you some details about our process of animating.
The first animation is about the relationship between the amplifier's positive input voltage and negative input voltage. From the animation, we can observe that when the negative input voltage of the amplifier reaches its maximum or minimum value, the positive input voltage of the amplifier would change state. This result also conformed to the previous theoretical analysis we made about the circuit. The second animation is about the input voltage of the amplifier and the current of the capacitor. From the circuit we construct, we can see that the voltage of capacitor is equal to the input voltage of the amplifier. By showing results with animation, based on the knowledge we have about capacitor, we can also confirm the fact that when input voltage of the amplifier is less than 0, the capacitor will start discharging. The third animation is about the output voltage of the amplifier and the current of LED. From the circuit diagram we built, we know that LED will light up when both voltages of LED and output is greater than 0. And in that case, the current of LED will be greater than 0 too, and the LED will be on. So by analyzing the time period of the output voltage of the amplifier, we then know when the LED light will be on and when the LED light will be off. So this is our circuit time clock. Thank you.
Because the time interval of the sampling data are not constant, so we need to sample again. Unfortunately, we have enough data, so there are not going to be a big error. And I create some list to resample the data and change it into ND array. Then we plot the result again. It's similar of the original one. Now it's animation time. Here is the animation part. We have the animations of some important parameters. Now we can observe that the Vout doesn't have the negative part, but output of the operation amplifier has the negative part. And because the currents are too small, so I use MA for the current and volts for the voltage.
Hello, this is Joyce again. This is our schedule for our future work. We're going to realize the entire circuit for our final project. So look forward to it. We're looking forward to it too. Well, that's my list. Hope you like this video and make sure to subscribe our channel. Bye!